welcome to the second day of QIP, and this morning our first speaker is Sam Roberts. He's going to talk about three Fermi topological quantum computation. So Sam, please.
Okay, great. Can you see my slides?
Yes.
Okay, great. Hello, everyone. Thanks for coming to the talk, and thanks very much for the organizers for putting on this great conference. Today, I want to talk to you about topological quantum computation using the so-called three fermion anyon theory. And this is work with Dom Williamson from Stanford and was primarily done while I was at the University of Sydney. Okay, first some motivation. So in recent years, topological quantum computation has been a primary focus for the path towards large-scale fault-tolerant quantum computation. Schemes based on the toric code, for instance, are very attractive for many architectures due to requiring only nearest neighbor connectivity with their qubits and due to their high thresholds and tolerance to noise. But while these schemes are great, they're still very resource intensive, and the overheads for universal fault-tolerant quantum computation remain formidable. This is in part due to many of the no-go results, such as Easton Canil and Bravi-Koenig and many others, which constrain the types of gates we can perform fault-tolerantly. So what we really want to do is to look for topological quantum computation schemes in a broad range of topological phases beyond the surface code and attempt to find new schemes that require fewer quantum resources. So to jump right into it, I'm going to cut to a brief summary of the main idea in case you fall asleep over the next 20 minutes. So in this talk, what we do is develop a general approach to topological measurement-based quantum computation using a certain class of 3D models known as the Walker-Wang models. And using these models, we can directly implement a computation scheme for a given abelian anyon theory using its symmetry defects, leading to a wide class of potential resource states. So what's the main idea? Pictured here is a schematic of how the computation proceeds. So we take one of these Walker-Wang models, which is defined by some input anyon theory, like the three fermion, which we'll explain in a minute. And we use its ground state as a blueprint for the computation. We identify one of the directions as simulated time. And then to perform the computation, we insert certain lattice defects and twist defects into the state, which are based on the symmetry of the anyon theory. Then by performing a bunch of single qubit measurements on the ground state of the model, we can drive the computation and generate a history state that encodes the topological quantum computation within. And so as a simple example, and perhaps a familiar one, is when we put the toric code anyons in, we generate the 3D topological cluster state scheme of Rausendorf and co. And so in this talk, we'll use the motivating example of the three fermion theory, primarily due to its conceptual simplicity. And at this stage, we really want to think of the model as being a nice stepping stone towards more general computation schemes. So don't worry if this doesn't make complete sense right now. The plan of the talk is to understand this diagram. So let's get into it. So what's an anyon? For the purpose of this talk, an anyon is just some particle excitation of a Hamiltonian that lives in two spatial dimensions. The most well-known and probably one that we're hopefully all familiar with is provided by the toric code, which is depicted here. So we have these plaquette terms and these star terms. So to stabilize a Hamiltonian, all of these terms are +1 in the ground space, but then we can think about creating excitations, meaning flip plaquette terms and flip stars, by using some string operators. And these excitations you can think of as particles, and indeed anyons, that have certain braiding fusion relations. So what's the property of an anyon? Well, there's a rich algebraic theory that describes these things. For our talk, we really need to only think about the three main properties. Namely, anyon theory consists of a set of particle excitations, labeled by this set here. These particles have some fusion rules, meaning what happens when we bring two of these anyons close together? How does the composite object behave? And they also have some braiding rules, meaning how does the system evolve as we exchange them or braid one around the other? So these anyons can be used for quantum computation. At a very high level, you can think about encoding quantum information into the fusion space of these anyons, of two or more anyons. You can produce gates by braiding them. And then to perform measurements, we simply fuse them. We'll see more of this as the talk goes on. So in this talk, we're not so much interested in the toric code anyon theory, but rather its related cousin, the three fermion theory. So the three fermion theory consists of 4 types of particles. We have this vacuum particle here, and then we also have these 3 non-trivial charges, which we label by red, green, and blue. These 3 non-trivial particles we'll refer to as fermions for reasons that we'll see soon. So these particles have very simple abelian fusion rules, meaning if we know the particles that go into the fusion, we can uniquely determine the outcome. And so in this case, every particle is its own antiparticle. So if we take 2 like particles, they fuse to the vacuum. And then 2 distinct fermions give rise to produce the 3rd non-trivial one. So for example, here we have red fuses with green to give blue. And these fusion rules are really just the kind of group operation of the Z2 cross Z2 group. So they're very simple. So simple fusion rules, how about braiding? Processes involving braids and exchange can be captured within 2 matrices known as the modular S and T matrices. As you can see from these diagrams here, in our simple abelian case, the modular T matrix is some diagonal matrix that captures the sign that arises when 2 like particles are exchanged. So time's moving upwards, and we can think about these particles as being exchanged. While the modular S matrix is a symmetric matrix that describes the sign that arises when, or the phase that arises when a particle is braided around the other. Now, this is a bit of a simplification, but for our purposes, it's fine. So for the 3 fermion theory, for the self-statistics, if we exchange any of the fermions, we get a -1 outcome, such as illustrated for the red guy here. And this is why we call them a fermion. And now for the S matrix, any process involving 2 distinct fermions will give a -1 sign and a +1 otherwise. So if we write out the full S and T matrices, we have the following. And anyone familiar with the toric code may notice that the only difference between the toric code and the 3 fermion theory lies in these 2 signs in the middle of the T matrix here. So the fusion rules are the same, the S matrix is the same, and the T matrices are almost the same. Now, you might think that modifying the toric code in such an innocuous way wouldn't have much of a consequence, but it turns out that this makes the 3 fermion theory quite non-trivial. In particular, the fact that all of the non-trivial particles are fermions leads the model to be known what's known as chiral, meaning you can't find this anyon theory as the excitations of some 2D projector model. So instead, to get a projector model, we have to realize it on the 2D surface of some 3D spin model, but more on that later. So how do we perform gates? Up till now, we have kind of a problem. The anyons we've considered so far are all abelian, and therefore they offer no computational power. All of the fusion outcomes can be easily deduced from the inputs, and the braids are all simple plus or minus 1 phases. So to actually perform computation, we need some other ingredient. And what we'll make use of are certain lattice defects, first introduced by Hector Bombin, and then known as twist defects. And I want to spend a couple of slides introducing what twists are and how they arise from symmetry. So to start with, let's consider the symmetry of the 3 fermion theory. The symmetry of an anyon theory is just some automorphism, meaning it's some permutation of the particle types that preserves the braiding and the fusion rules. For the 3 fermion theory, all of the fermions behave exactly the same. So we're free to relabel them. And this relabeling can be thought of as an S3 symmetry. So the symmetry group, the permutation group of 3 elements. And we write the elements of this symmetry group in this standard kind of cycle form, where, for example, RG is the permutation that swaps red and green fermions, and then RBG is the one that cycles through the red, blue, and green gas. So if we have a symmetry of the anyon theory, in some cases, you can realize it as the symmetry on the lattice. So remember, we're always thinking about some underlying Hamiltonian there. And there are some subtleties for this, but for our purposes, we just assume everything works fine, and we'll see more on this later. But in particular, if you have this symmetry, you can create a domain wall on the lattice that implements a symmetry action. So recall that we're imagining that these anyons live on some 2D lattice. In this case, it may be the surface of some 3D model. And you can transform the Hamiltonian along a one-dimensional region indicated by this dashed line here, such that whenever you have an anyon that moves from one side to the other, a symmetry action is induced on it. So for instance, here, green turns into red as it goes along. These strings denote the kind of world lines. Such domain walls are terribly interesting on their own right, as for instance here, you can just think about the domain wall as just relabeling the anyons on one side. But what is interesting is if you consider cutting open a domain wall such that it terminates into some zero-dimensional point-like regions, as indicated by these crosses here. And the point is that these points we'll call twist defects, and they come in pairs, and they correspond to elements of the symmetry group. In terms of the Hamiltonian, one can think of these twists as being like a lattice defect, such as a dislocation or a disclination. But at this stage, it doesn't really matter too much what they look like. And it turns out that these twists themselves behave somewhat like anyons, a bit seemingly immobile. They have their own fusion and braiding rules. And fascinatingly, they can be, and in our case for the three fermion theory, they are non-abelian, even though the underlying anyon theory is abelian. And another important property of these guys is that they have non-trivial interactions with the underlying anyon theory. So in particular, if you braid an anyon around the twist, a symmetry transformation is implemented. So this is a bit high level, I realize, and a bit abstract, but we'll return to the issue of twists later on the lattice. So encoding in symmetry defects, so I claim that these twists are non-abelian, they have non-abelian fusion rules, and so we're going to use them to encode our quantum information. So there are qualitatively two types of twists corresponding to whether you have a kind of 2-cycle element or a 3-cycle element. And when you fuse a twist anti-twist pair, you get some outcome that's some element of the three fermion theory. So for example, here, if we fuse these red-green swapping twists, if we fuse together two of those, we can either get a vacuum as outcome or a blue fermion. And you should think about these two outcomes as defining a basis of some logical qubit. And then the simplest way to encode is to utilize two pairs of twists as schematically shown here. Information is encoded within the fusion outcomes of any pairs of twists. And you can think about when you fuse different pairs as being different bases measurements, so measurement in different bases. And to make this concrete, you can think about performing a fermion braiding process that detects the charge within these two twists. So for instance, create a pair of red fermions, braid one of them around the pair of twists, and then annihilating it, we can measure any blue charge within those pair of twists. And then you can define the string operator that does that process. So that's indicated by this red guy here, some string operator. And then you can do the same for the other pair. And you can define these two guys as anti-commuting canonical pairs. So we can call one Z and one X, and they have the correct anti-commutation relations as defined by the three fermion braid relations. Okay. So now I just want to claim without proof that the symmetry enriched anyon theory is Clifford complete, meaning we can braid and fuse twist defects of the three fermion theory to generate all Clifford operations. I think this computation scheme is quite nice, and unfortunately I don't have a lot of time to go into the details, but the main idea here is that all of the Clifford unitaries can be achieved by certain braids. So a generating set of which is illustrated at the bottom here, where we think of these strings as the world lines of some twist defects, and again, up the page is kind of forward in time. And while we only get Cliffords in this case, I think it's still quite interesting because when we compare to the toric code theory, the toric code twists are not Clifford complete, and you need some other ingredients to complete the Clifford group. And feel free to ask me more on this later. But what we can do is we can compile these braids into more natural diagrams showing the locations of the domain walls and the twists, and where again, we think about up the page as moving forward in time. And again, we can, what we can do is standard, we only have the Clifford group, we can use magic state distillation to obtain our fault-tolerant non-Clifford gate. So this is just kind of standard, not that super interesting. I just want to focus on the topological aspects for now. So the point of this slide is to really just show that certain twist configurations are sufficient to generate all Clifford operations. And apologies for not providing too much intuition on this. But what we want to get into is more the three fermion, the Walker-Wang aspect. So we have our three fermion theory, we have our twist defect theory corresponding to the S3 symmetry, and now we have our computation scheme. But how do we actually realize the computation scheme in a physical setting on the lattice? So now we can get into the main result, which is exactly that. So if you got a bit lost in the whole twist business, we're going to change gears now, so it's fine to jump back in. So let's define the Walker-Wang models. So this is a class of models first introduced by Kevin Walker and Zhenghang Wang in 2011 to describe some new types of topological phases in 3 dimensions. And if you're familiar with the Levin-Wen string net models, then these are kind of a natural generalization 1 dimension up. So the input to the Walker-Wang model is an anyon theory, meaning some set of particles with braiding and fusion rules, along with some discretization of a three manifold. And then at a high level, for this given input theory in lattice, the Walker-Wang construction prescribes a commuting projector Hamiltonian whose ground state looks like weighted superpositions over all, not all, but some braided anyon diagrams, particularly those that are closed. So you can think of these configurations that appear in the superposition as world lines of the underlying anyons that you put into the theory that are undergoing some braiding and fusion, and more on this later. But an important property of the construction is that if you choose a manifold with a boundary, then the anyon theory that you put into it appears as the deconfined excitations on this surface state. So in other words, the Walker-Wang framework provides a constructive way of realizing some 3D models that have the desired anyon surface state. So we can be a bit more precise using the three fermion theory as input. And I want to point out that this model was studied in a really nice paper by Bernal et al. So for the three fermion theory, we consider a cubic lattice as our discretization, and on each link we will have two qubits. So we have two qubits because we want a four-dimensional vector space on each link, corresponding to the four species of anyons in the three fermion theory. So we can associate each of these four basis states here with the presence of a fermionic string of the three fermion theory. So for example, if we choose this sigma here and this tau here to label the two qubits on each link, then the eigenstates of the local Pauli X operators label the presence of different anyon types in this way. So like a link hosts a green fermion whenever the basis is plus minus. And we can think of, we call these links when they're in these states as being occupied by a fermion, as a fermion string. And we can think of these as small components of a fermion propagating in space-time. So it turns out this model, you can realize it as a stabilizer model that is a commuting Hamiltonian whose terms are Pauli operators. And I've depicted some of these terms down here, and I don't want you to worry too much about the details. They're not important. The main thing I want you to notice is that there's just two types of terms. So there's these vertex terms, and there's these plaquette terms, and they're both Pauli terms. Okay, so while the Hamiltonian is not super important for our purpose, the ground state definitely is. And it takes on a particularly elegant form. So if we choose a closed manifold, then there's a unique ground state. And as I mentioned, the ground state should look like superposition over all closed anyon diagrams. So let's add a bit of color to make sense of this statement. So taking the basis to anyon identification as we've shown here, we first know that every configuration in the superposition must satisfy valid fusion rules. So since the three fermion theory is abelian, this is quite easy to understand. At each vertex, the anyon flux must be kind of conserved. So for example, here, these red lines form closed strings, but you can also have a red line branching off into a green and a blue. So this is satisfying all of the fusion rules at each vertex. Now, what about the coefficient? So there's the coefficient here. These are all the configurations. This is where the braiding rules enter. So each configuration is simply weighted by a plus or minus one sign that's determined by the braid relations. So you can check if two configurations are related by some elementary braid or exchange, then their sign can, they must come in with different signs as determined by the braid rules, for example, here and here. And you can kind of simplify this whole thing and relate the overall coefficient to some quantity in knot theory. So we know it as the linking number and the Reith number. This is a little bit subtle, and the main message is really just that the sign is plus or minus one, depending on the configuration. Again, at a high level, we can think about these properties as arising from the Hamiltonian terms as follows. So the vertex terms are there to enforce fermion parity. So this guy here, it says the number of red and blue guys surrounding a vertex must be even. It's just the sigma x's. And you can see that the sigmas only check these first guys. While the plaquette terms can be thought of as fluctuating between different configurations with the appropriate signs. So they create kind of small loops of fermion, and then the signs come in depending on the neighborhood. Okay, so we have the Hamiltonian, we have the ground state, and now we're kind of ready in a position to understand this cartoon picture of how the computation scheme works in a very simple setting, namely the one where we don't have any symmetry defects. So we take this 3 fermion ground state. So let's just consider it on some periodic boundary conditions. And let's consider this blue region here where we want to measure all the qubits within this blue region. So let's consider measuring every link within this blue region in the local anyon basis, which in our setting corresponds to measuring single qubit Pauli X operators on all of the qubits. And then each of these measurement outcomes is in general random, and we obtain two bits per link. And these bits correspond to the presence of the corresponding fermion string. So collectively in this blue region, all of these outcomes correspond to the post-measured state belonging to some fixed anyon spacetime configuration according to this standard basis labeling. So while the bulk was a superposition over all of these different configurations, we can think about the measurements as just fixing out a particular one. So all of these measurements aren't completely random. In the absence of any errors, the post-measurement state must satisfy this fermion parity conservation on each vertex. And we call this post-measured state the history state. So it looks like some braided diagram of the 3 fermion theory. So what about the boundary of the measured region? Turns out what we've actually prepared on this boundary is a 3 fermion surface state, namely the stabilizers that you get on the post-measured state specify a 3 fermion surface topological order with some random configuration of fermion excitations. So this surface state is where the information is going to be encoded once we have all the twists and everything, and this surface will be propagated by the measurements. So in general, these fermions on the surface, they can propagate around randomly, and unless we account for them correctly, they can ruin the computation. This is a bit of a subtle point, but the solution is that the location can be directly deduced by the history state, and as such, we can just account for them by performing a Pauli correction where appropriate that's conditioned on the measurement outcomes. And keeping track of a Pauli frame in this way is very standard in measurement-based quantum computation. Okay, so we have our surface state. To perform logic, we need to create some domain walls and twist defects in the model, and this is what we'll now show. So if you want to have some circuit, we can think about this circuit. We need to print in the right defect configurations to simulate this circuit using these kind of gates that I mentioned a few slides ago. So first, in order to define defects in the model, we need to promote this S3 symmetry of the anyon theory to a symmetry of the Hamiltonian. So in other words, we need to find a representation of the symmetry on this lattice such that it leaves the Hamiltonian invariant. And I won't go into much detail, but you can show that this unitary can be done. And it's realized there's a local Clifford operation acting on each link to perform the correct fermion permutation. But then we also need potentially a global translation. So let's consider the simple case of creating a domain wall. So let's take a region here, let's say this right-hand region, and we consider restricting the symmetry to that region. And if we apply this restricted symmetry to this region, then it leaves the Hamiltonian within the interior invariant, since it's a symmetry of the Hamiltonian. But what it can do is it can result in some modification to the boundary of that region. So all the terms along here can be modified. And this modified region on the boundary defines a domain wall that exchanges the fermion world lines according to the symmetry element as depicted here, right? So for twists, the story is only slightly more complicated. To create a twist, we consider truncating the domain wall. So then on this one-dimensional region, we need to recover a complete set of Hamiltonian terms. But since we have a stabilizer model here, we can just find some maximal abelian set of terms that commute with the bulk Hamiltonian and the surrounding domain wall terms. And then because it's all the terms are local and we have translational invariance along this one-dimensional region, we can find also a translationally invariant set along of terms along this twist to add back in. And we make use of a theorem of Haar and company here. So importantly, what's happening here, we can see that by braiding, we can see that we've really created the correct object here, this twist defect, because we can braid a fermion string in, such as this green guy coming in here, braids around the twist, and it's exchanged according to the symmetry. So this twist would correspond to some 3-cycle symmetry. So green, red, blue. Now for the fault tolerance of the scheme. So up till now, we've not really considered errors, but of course, errors may occur during the resource state, preparation, computation, and measurement. But for concreteness, let's just consider what happens if we have some Pauli errors to the state prior to measurement. So once again, the Walker-Wang state picture affords us a particularly elegant way of viewing errors. In particular, such errors result in modification to the observed history state. So they can be thought of as locally fusing in some small string segment to the history state. But as we discussed before, the history state, in the absence of errors, should satisfy fermion parity at each vertex. So in this way, Pauli errors will generically result in violations of the fermion parity, and we can detect their presence. So we refer to some vertex that doesn't satisfy fermion parity as a syndrome. So it's here and here. And in this example, let's consider this configuration where the solid lines are observed outcomes and the solid nodes correspond to vertices where fermion parity was not satisfied. And then in this way, the dashed lines correspond to possible errors that may explain the syndrome. And if you prefer an operator point of view, you can think of the syndromes as corresponding to the outcomes of these vertex operators displayed on the right, which should be +1. And whenever the outcomes give you a -1 outcome of these vertex operators, then you say there's a syndrome. And then to decode, we just need to come up with some recovery string configuration that restores parity. And we can make use of all of these well-studied techniques for the toric code, such as minimum weight pair matching. And then how do we know when the decoding succeeds? Well, if we decode, we don't need to come up with the exact error configuration, only a homologous one. So in particular, if the combined effect of error and recovery operation results in a fermion being exchanged between distinct twists, then a logical error has occurred, such as here. Let's say that's the combined effect of recovery and error. But there's many benign errors, such as these small loops that don't cause any harm. You might be thinking this problem is very similar to that of the toric code in 2+1 dimensions, and you'd be absolutely right. It's exactly the same. And in this simplified setting, using some toy error models, we can find that the bulk decoding threshold is exactly the same as the topological cluster state model. Now, number I wouldn't put too much weight in this number. It doesn't mean too much. It's really just meant to say at 0th order, the kind of error correcting behavior of the two models is the same, but under a more realistic noise model, they may differ. So I'm just this is the last little remark that I'll make before wrapping up. I just want to remark that the implementability in practice. So while we've considered all these 3D states, we really want to think of one of these dimensions as simulated time. And as such, we only really need to create and measure the Walker-Wang ground state in constant width windows, and that is thus implementable in a 2D scheme. This is very common in measurement-based quantum computation, and I just want to emphasize it. Okay, so to wrap up, we've shown that the Walker-Wang framework provides a really powerful tool to generate new measurement-based protocols. And in this talk, we've shown how to implement a new scheme based on the 3 fermion theory. So really hope that this example provides some intriguing step into topological quantum computation using more general schemes, and perhaps even a launch point to study more non-stabilizer models. And moving forward, I guess I'll just mention one of these points. I think it would be interesting to push on the applicability of this approach to non-abelian theories. Maybe we can use some of the tools developed by Alexis and collaborators in his talk earlier on the Fibonacci. But one of the difficulties here is in the controlling of the randomness of the measurement outcomes that comes up in MBQC. Can be in general much more difficult if we have a non-abelian theory and computationally expensive. And perhaps an adiabatic approach may be suitable here, where you can essentially kind of project into the known outcomes. But with that said, yeah, I think I should probably wrap up because I'm running out of time. But thanks very much, everyone, for your attention. And yeah, if there's happy for any questions.
So thanks, Sam, for the talk. So I just pick up one quick question. So how does one actually enforce the symmetry in practice, you think?
Enforce the symmetry?
Yeah.
Which symmetry are we talking about? So this fermion parity symmetry that arises, it's really just a term in the Hamiltonian that means when you have the ground state of this model, it's satisfied. So really the ground state of this model automatically satisfies this fermion parity symmetry. And then yeah, errors can obviously break this, but that's what the goal of decoding is. So I guess you can think about the decoding as kind of recovering the fermion parity symmetry, if that's what you're meaning.
Okay, thanks.
Thanks.